Hello, my name is Bob Varney, and I'm a software architect with Radian Memory Systems. I've been working here for the last several years on host-resident software for flash management, and today I'm going to tell you a little bit about our block translation layer. Our block translation layer, or BTL, was developed to enable flash zones to be treated as conventional zones. We developed this initially for the Linux kernel and recently ported it to SPDK, the Storage Performance Development Kit. Today we'll provide an overview of the use cases and architecture, discuss what was involved in the port, and then review performance results. For our agenda, we'll discuss why you might need a block translation layer and what the Radian BTL in particular can do. Then we'll dive into the architecture of our BTL that was developed first for the Linux kernel, but in a way that we hoped would allow us to port it easily to other host environments. So we'll then describe our experience in porting it to SPDK. Finally, we'll explore the performance of the SPDK BTL relative to the kernel BTL. So why might you need a block translation layer? Well, applications can be overwriting or non-overwriting. Relational databases tend to be overwriting, like Oracle or MySQL, while NoSQL architectures are more likely to be non-overwriting, like Redis or Cassandra. As most people know, NAND flash does not support in-place updates and wants data to be programmed sequentially. But what's less recognized is that in data centers, storage devices are typically shared over multiple servers, virtual machines, and applications, and the provisioning and management of those shared storage resources has to be handled by an intermediate storage management layer. This can be in the form of network-attached storage, SANs, and all-flash arrays, or software-defined storage frameworks. Even in recent hyper-converged approaches that combine server and storage resources in the same appliance, these local storage resources are typically shared over nodes in a cluster, and that distributed access is handled by a storage management layer. So whether the application is overwriting or non-overwriting, it is most likely going to be going through a storage management layer because it's most likely going to be accessing shared storage. The large majority of storage management layers are non-overwriting, meaning that they do not overwrite data in place. This can take the form of copy-on-write or log-structured variants for reliability and performance, and some form of append-only approach is common to achieve efficient scalability. But whatever the objective, the fact that these storage management layers are typically non-overwriting aligns very well with the NAND flash media's requirement for non-overwriting. This leads to software-defined flash SSDs that Radian has pioneered for several years, which do not have complete FTLs embedded in the SSD. With Radian's cooperative flash management SSDs, ranging from the symphonic and zoned flash product lines to support for the NVMe industry standard zone namespaces interface, non-overwriting storage management layers can directly handle data placement and garbage collection without any intermediate embedded FTL or host FTL. But there are exceptions. Some storage management layers may be overwriting, and some data center deployments may still use direct attached storage, where an overwriting application accesses local storage devices directly. While this is becoming increasingly rare, a more common case can be found with a distributed file system like HDFS or an object layer like Ceph, as seen here on the left of the slide. These are append-only, non-overwriting architectures, but they depend upon a local storage engine to sit below them, between them and the SSDs. This local storage engine could be something like certain RocksDB variants, which are mostly non-overwriting but sit on top of an external overwriting file system and would need some flash translation layer support, or other RocksDB variants that can internalize the file system abstraction and more directly interact with a non-overwritable flash without an intermediate external file system, other than perhaps for logs or metadata. That flash translation layer can also reside inside the SSD, as found in a traditional SSD, or in a host-based flash translation layer, like BTL. Another example configuration involves a non-overwriting storage management layer accessing the flash directly across nodes for primary data accesses, but using an overwriting local file system for internal system management, performing services like backup, which requires a translation layer. In yet other cases, largely non-overwriting storage management layers may actually have requirements to overwrite some metadata in place. This type of configuration is similar to the previous example where an in-kernel file system is used for local system maintenance, but differs in that the performance requirements for these metadata regions can be critical to system performance and have high churn, requiring not just a translation layer, but a high-performance translation layer. And we have requirements related to compliance and qualification testing, specifically with JESD 218, that defines requirements for testing SSD endurance and data retention. This method uses a standardized representative workload described in JESD 219 with a defined distribution of payload sizes and a defined distribution of accesses across the LBA space. Devices are written to their full endurance under various thermal conditions and then tested for data retention. And these standardized workloads require overwriting patterns. To our knowledge, the RMS 350 is the first zoned flash SSD to pass a JESD 218 qualification, and it is targeting compliance with the NVM Express specification for zone namespaces. To recap, software-defined flash and Radian as a company have had several application requirements for a block translation layer, including the ability to target DAS configurations when overwriting local file systems are used as the local storage engine under distributed systems like HDFS or Ceph, when overwriting file systems are used for local system maintenance, to support storage management layers that update metadata in place, and to emulate purpose-built storage management layers and other typically overwriting workloads for the purpose of system testing and SSD qualification testing. The Radian block translation layer is designed to improve the alignment between application workloads and underlying flash media. With the BTL, we can build conventional overwriting block devices or other non-overwriting zoned devices out of a variety of target drives, from standard FTL SSDs to Radian zoned drives. The BTL's log-structured design serializes writes through a logical to physical address mapping and has an associated cleaner that performs garbage collection to create contiguous free space. It also contains an integrated scheduler and a write cache. The idea is that by lifting the FTL logic out of the drive and making it a software layer running on the host, we now have a better chance of configuring it to suit the needs of the application, configuring aspects such as granularity of writes and cleaning, and policies for scheduling, for example. Since the BTL is designed to work both with conventional SSDs and collaborative flash drives like Radian's, we can in a configurable way take full advantage of the storage capacity and physical parallelism in the drive, as well as any other features unique to the drive. So using the BTL with Radian drives provides additional benefits. Write amp is reduced because over-provisioned capacity is accessible to and fully utilized by the BTL cleaner. It is not captive inside an FTL SSD. And Radian's delegated copy move allows copy operations to be offloaded to the device. And performance-isolated namespaces allow multiple performance-isolated block devices to be created from a single drive. The BTL can construct block devices out of target drives in a number of different ways. In their simplest forms, block devices can be created from single targets, or in the case of a Radian drive, from a single namespace with some associated NVRAM. Radian's NVRAM appears as an exposed namespace that is analogous to the internal NVRAM of a traditional FTL SSD. And so the exposed NVRAM can be used by the BTL as a write cache or a write-ahead log. But the BTL can also be configured to work with conventional block devices, FTL SSDs, and other zoned drives. If a drive is subdivided into multiple namespaces, these namespaces can be used to make BTL devices, such as by creating multiple BTL devices on a single drive, or a single BTL device aggregating multiple namespaces on a single drive. Multiple drives can also be aggregated into a single BTL device, as shown here in a single host scenario, or in a dual-ported scenario where each drive is split into two namespaces, and these halves are then aggregated into a multi-drive BTL block device on each host. Now that you have some idea of what we're trying to accomplish with BTL, let's talk about its architecture and where SPDK fits in. As mentioned earlier, the BTL has a log-structured design that serializes writes through a logical to physical address mapping with an associated cleaner that performs garbage collection and creates contiguous free space. It also has an integrated scheduler and a write cache. The BTL can aggregate or partition multiple varieties of underlying drives, thereby creating the overwritable block devices seen by the storage management layers or file systems above it. We knew when we started that we were going to want to have use of the BTL in the Linux kernel and in user space environments. So a fundamental aspect of the architecture from the beginning has been a clean separation of the BTL core from what we call a BTL host adapter. The core represents the bulk of BTL functionality and should compile and be unit testable in user space. And the interface it defines with its host environment should be general enough to be implemented in any sufficiently powerful host environment, with Linux and SPDK as two initial target platforms. Another user space environment variant we've considered is one based on the IOU ring interface for Linux I/O, but we haven't had a chance to integrate support for that yet. BTL enables the construction of devices where each device consists of a number of slices running in parallel, and each slice is a network of request processing services built on top of an event-driven, non-blocking, and lock-free substrate. The acronym PIL here stands for Programmable Injectable Layers. It's just a submodule of BTL, the event-driven substrate on top of which the services are implemented. Requests from outside of BTL are then injected into the core from the host environment and ejected from the core to the underlying target devices. The current BTL services we've implemented are shown here. This isn't intended to be a closed set of all services you might need, but it has proven to be fairly versatile thus far. The idea is that we could easily add more services or potentially make it possible for users of BTL to write their own and plug them in. Inject and eject are distinguished services that are used in every device type. The SFMX service is also used as the bottom layer for any final address translation and eject command marshalling. And the use of the remaining three, the overwrite service, zonewrite, the non-overwriting service, and PNV, the NVRAM service, well, that will depend on what kind of device functionality we're constructing. Each service is defined by a set of requests or commands it implements, such as various kinds of reads or writes, and certain types of requests are expected to be supported by whatever service is the receiver of injected commands. And those expectations vary depending on the type of device that's been constructed. Each service command is just a function like the one shown here, accessed in the usual manner via a table of function pointers. And the service command ultimately just manipulates some internal state, may or may not generate other subordinate commands based on the command it received. These commands can be thought of as asynchronous command chains. Most commands transform their arguments in some way and dispatch derived chains of commands that usually include a next command that the command itself received, which ultimately encapsulates the command representing a callback to the host environment. In the simplest service stack, we just have SFMX. No overwriting, caching, or use of DCM. Just the optional use of ASL translation based on the ASL configuration or address space layout of a Radian device. This is in order to distribute writes from a sequential logical address stream across the physical address space in order to ensure maximal physical parallelism. Next, by adding the zonewrite and PNV services, we add caching or write buffering and use of DCM on top of the basic non-overwriting layer that SFMX provides. This provides a non-overwriting layer with write buffering and optional DCM. Finally, in front of zonewrite, we add the overwrite service, providing an overwritable address space with support for cleaning or garbage collection. And now, in this scenario, if we are using a Radian device, DCMs would be used both for writes and for copies. Well, the services we just talked about define the core logic of BTL. They don't implement everything that they need directly, of course. All of them rely on a number of other utility components to do much of the heavy lifting. And so we have GC for garbage collection, resource for the handling of parallel subsets of namespaces for write streams and for address management, schedule for scheduling, config for configuration specifications, space for dimensions of stores, frame types, and various address mapping abstractions, BTL STD for standard argument types used in the individual requests and for service request APIs, and PIL, as mentioned, for several more fundamental types and for the asynchronous execution engine that BTL is based on. All of these components are part of the BTL core, which means that they're generic and independent of any host environment, and no modifications of any kind should be required to work in a new host environment. At least that has been the goal and the theory behind BTL's design. So let's see now how well things held up in the port to SPDK. SPDK, the Storage Performance Development Kit, is a set of tools and libraries built on top of DPDK, the Data Plane Development Kit. It consists of user space pulled mode drivers to reduce the overhead associated with the use of the kernel. The I/O path is lock-free and based on message passing, and it provides a passive pulled mode NVMe driver that also runs in user space. SPDK was started at Intel in 2013 and open sourced in 2015, and you'll find some links here below for more information. So why would someone want to use SPDK? Well, using polling instead of interrupts can improve performance in certain applications, such as with low latency devices or even in applications with high IOPS because of the overhead associated with a high interrupt rate. And by devoting more CPU cycles to storage work, SPDK throughput is supposed to scale better as you add devices for a given number of CPU cores. To understand everything in BTL that might have needed some attention in the process of porting to SPDK, it's useful to start by just listing and categorizing the key abstractions that are involved. Ultimately, the BTL core needs some way to map requests from the host environment to and from BTL. These requests are processed on some threads of execution and on some processor cores, and some are I/O requests directed to specific target devices. Then, of course, there's memory allocation and time for tracking elapsed time and for delayed execution. So the abstractions shown on the left are the fundamental ones that BTL needs the host environment to implement for it. BTL defines an interface for each one, and the SPDK port essentially had to implement each one of these according to that interface. Those listed on the right side, however, are internal abstractions making up the bulk of the BTL core. These are implemented generically and have no compile time dependencies on any host environment specific artifacts. There's no references to host environment include files, not even ifdefs in the things on the right. The only additional step that may depend on the host environment is how the files are compiled, because the C compiler switches are different depending on whether the resulting machine code is going to be used in static or dynamic libraries, or whether it's going to run in user space or kernel space address ranges. But the source code for constructs on the right is truly common across hosts. All we had to do with these core components in the SPDK port was to write the makefiles needed to compile them into the libraries we wanted SPDK applications to use. And in that respect, the BTL architecture worked as we had hoped, and the port to SPDK was straightforward and incremental in effort. So creating a host environment for BTL involves mapping the host native constructs for things such as threads, memory, and devices to the abstract BTL environment API that the BTL core will depend on. This is fairly straightforward. For example, the slide shown here illustrates just some of the kinds of details that have to be dealt with. There are a few different pieces in the Linux kernel's representation of a blocks device, for example, one of which is a set of virtual function tables that must be set up for standard block device operations. The corresponding construct in SPDK is what's called a BDEV, and like the kernel, one defines a BDEV in part by defining and registering tables of functions. Ultimately, the task of creating a host environment involves mapping these environment-specific constructs to BTL's generic types for the same abstractions. The generic core of BTL then accesses the mapped construct through the generic type. And we continue with this sort of porting process for each of the host environment abstractions, and as a result we now have two host environments, one for the kernel and one for SPDK. The BTL core can be wrapped up as a Linux kernel module, in which case its devices appear as block devices to the kernel block layer, and it relies on targets that are also block devices in the block layer. Completions now flow back to BTL via interrupts, but the BTL core is oblivious to how they're being delivered. They all just show up eventually as BTL commands. And similarly with the SPDK host environment for BTL, a BTL block device appears as just another BDEV. Now, SPDK's polling mechanisms are delivering responses back to BTL, but again, the BTL core doesn't really know or depend on that. It just sees the resulting commands. Also, note that the bottom level BDEV, the target of BTL, could also theoretically be a zoned BDEV. But by the time zoned BDEV support was released in SPDK last October, we had already developed much of the lower layers of BTL with the NVMe BDEV. We hope to add zoned BDEV support as a BTL option in the future. So the port has gone fairly well, but we did face some challenges. A few bugs were found that hadn't shown up under use with the kernel environment. The configuration and administration aspects of BTL were implemented largely in the kernel host environment, and getting these to work in SPDK ultimately involved refactoring some of the synchronous code that we had written into asynchronous form, and we realized that the code could have been implemented in the BTL core. Finally, there were some issues we ran into with thread management. We discovered that not all the SPDK apps handle threads the same way, and we had to do some extra work to ensure that the right event loops were created on the right cores. The problem stems from the way BTL abstracts cores and threads and how these abstractions are concretely assigned to physical cores. In the kernel environment, there was no actual per BTL thread processing associated with any of these. But when we naively mapped our abstract threads to SPDK threads containing event loops, we had too many event loops on individual cores. This was further complicated by the fact that different SPDK apps manage threads differently. SPDK defines a set of utilities for SPDK applications that involve reactors, and the reactor manages the event loops, but with the FIO plugin, the reactor mechanism was not used. This led to the need for different thread modes, one where the event loop creation was delegated to the reactor mechanism, and one where the BTL host environment for SPDK can create them as needed. So right now we have 3 example SPDK applications that we've constructed using the code in the SPDK source code as a starting point, the FIO plugin, the iSCSI app, and NVMe over TCP application. As far as the porting effort, if we try to tease apart the actual development, integration, and testing from the performance evaluations and other BTL work that was going on in parallel with SPDK work, this is what the effort looked like for the port. The numbers in the bars are person weeks. We started the work at the end of last summer, and by the end of the year, the system was functional for single devices. Support for multiple devices came somewhat later. Let's now look at the performance of BTL using SPDK versus BTL using the kernel. As I mentioned earlier, SPDK's value proposition is that by being more CPU efficient, that frees up more CPU capacity to be used for other things, such as implementing your storage stack. We'll say more in a minute about what CPU efficiency really means in the context of SPDK. The other aspect is that SPDK reduces latency through polling. Intel's performance reports have claimed a 6 to 8x improvement in throughput scalability for SPDK versus the kernel in terms of how many SSDs can be handled by a single CPU core. They also report mean latency improvements of 10 to 20%. So we set out to measure the performance of BTL using SPDK compared to BTL using the kernel. For this, we started with our normal device comparison tests. These are the same tests we have used to compare 2 device models in the past, normally running under the same host environment. And these tests were originally designed with the hope that the performance measured by the test would be determined by the device and not the CPU or the software stack running on it, because we wanted to measure the device performance. These tests involve hours of preconditioning followed by a series of various 15 to 20 minute workloads generated by FIO. So our first SPDK versus kernel comparison was to run one device model under two host environments, shown here for a single drive and a 6-drive configuration. The chart shows one of these results, the throughput comparison with a random 4K, 70% read, 30% write workload, and a queue depth of 32 per drive. We see that SPDK does improve throughput here, but not by a factor of 6. The results for latency are similar. We see a small improvement for SPDK versus the kernel. So what happened to the 6 to 8x improvement in throughput and 10 to 20% improvement in latency? Well, as I mentioned, this first test was designed to compare devices, not host environments. And the host environments we want to compare differ mostly in their use of the CPU. To compare host environments, we need some new tests that were more consistently limited by the CPU and not the device. There are many things to keep in mind if you want to compare a set of test results. Obviously, the device and CPU are important, but equally, if not more important, is which of these is actually limiting the performance observed in the test. Also, has the device been preconditioned? In other words, has it reached a steady state in terms of any garbage collection that is going on? Or is it in a fresh state? This is important because if your write amplification peaks at, say, 2x or 3x, then your performance, as observed by the workload generator, may vary by that amount when you compare the clean device performance with the preconditioned performance. That is, if your test is device limited. And CPU consumption may increase disproportionately due to this GC that is behind your write amplification. The workload generator itself also matters, especially when CPU is limiting the test. Intel reported performance variations on the order of 70% when different workload generators were evaluated. And what software stacks are we really comparing here? Saying SPDK versus kernel doesn't quite tell you enough, because Linux scheduling algorithms may vary and there may be multiple options for the NVMe driver in the realm of SPDK or the Linux kernel. Intel reported, for example, about a 30% performance difference between stacks using the polled mode driver and the NVMe BDEV, which we use in BTL. And then there's BTL itself, which represents yet another increment of CPU consumption above and beyond the CPU consumption of the host environments we're trying to compare. With this in mind, should we also expect a 6 to 8x improvement in throughput and a 10 to 20% improvement in latency when we compare BTL on SPDK to BTL on the kernel? Well, no, and here's why. Certainly, if we're using device comparison tests that are device limited, any difference in performance due to what is happening in the software stack will be reduced. So let's assume that the devices are the same and the CPUs are the same, and the test is not device limited. First, let's imagine running at some fixed throughput x less than the device limit and less than what each CPU can deliver. Each software stack consumes some amount of CPU to deliver throughput x. The diagram shows two stacks, A and B, each superimposed on a bar representing the total available CPU capacity of some CPU or number of CPUs on which each of the tests was run. The full height of the bar represents an effective utilization of 100%, shown here as U equals 1. Thus, the height of each software stack represents the relative amount of CPU time it consumes for that fixed amount of throughput, which we set to x. So in this diagram, stack B is more CPU efficient than stack A because it's shorter. Assuming we can measure these stack heights somehow, we can predict the throughput of each stack at its maximum, assuming now that the CPU is still limiting the test. Then we could predict the throughput multiplier, the ratio of maximum throughput from one stack to the other. And it's just the inverse of the ratio of their effective utilization values. One other technical complication I'll mention here is that when you're trying to measure the CPU costs of these two stacks, is that you can't really use a traditional CPU utilization measurement if SPDK is involved, because SPDK uses polling, which consumes all CPU by design. That is why I said effective utilization. The equivalent notion for SPDK would be something like, what proportion of its event loop iterations do useful work versus doing nothing? Traditional CPU utilization measurement is a valid way to get the cost of what is running on the stack for the kernel, assuming it is not polling. What you can do, however, is run a CPU-limited test. In this case, the height of the stack is the independent variable, u equals 1, and the bandwidth it produces will be different for stack A versus B. So if we find the max throughput that the weakest stack can deliver through a suitable CPU-limited test, at that throughput level, stack A will consume all of the CPU, while stack B at the same throughput would have capacity to spare. If we imagine stack A represents the kernel and stack B represents SPDK, then at the throughput level that saturates the CPU with the kernel, SPDK would leave excess CPU capacity available for other use. That is the essence of the CPU side of the SPDK value proposition. So if we compare a kernel-only stack to an SPDK-only stack with a workload generator like FIO on each, we can determine the throughput multiplier, and this quantity is essentially what Intel is reporting when they report throughput multipliers of SPDK. That's represented by these bars on the left. What happens to this if we add another layer that consumes additional CPU? This is shown by the delta layer in the two CPU boxes on the right, its height representing the CPU cost of that layer per unit throughput. The net effect is that both stacks get a little bit larger, and both stacks have a lower maximum throughput than before, and so the throughput ratio of the two larger stacks is reduced. A similar line of reasoning applies to latency. For example, if we see a certain relative latency difference when the software stack involves just kernel or SPDK, the latency reduction percentage will be lower when we add the fixed additional latency of a real device in an additional software layer. So we designed a series of experiments where the CPU was always the limiting factor, and we varied both the layers involved and the functions those layers were performing to determine the relative CPU cost of the stacks. In this diagram, we show the results from BTL plus SPDK versus BTL plus the kernel for 100% read, 100% write, 4K random with FIO as the workload generator, and everything else about the test the same across the two systems being tested. We varied the functions that BTL was performing by varying not only read versus write, but also write in a fresh state before any GC versus write in a preconditioned state with GC occurring. So the effect there is more than just the additional I/O, which can be computed by knowing the write amplification. The nature of the work the CPU does during GC is different per I/O and costs more. All CPU service times were measured per meg of throughput, but are shown here as dimensionless quantities relative to the value for 100% read. What we can see here is that the CPU time of the kernel, the blue bars, is always larger than the CPU time of SPDK, the red bars. We also see that both bars increase and get closer together as we advance across the different workloads, because the workloads from read to write plus GC require, by design, incrementally more CPU. The net result of this is that the throughput multiplier represented by the black line converges toward 1. Everything else being equal, the more constant functionality or work we add to the stack on top of the host environment layers, the less of a difference we should expect to see in the overall performance of the systems involved. So instead of a 6 to 8x improvement for 100% read, we see a ratio of about 3.6x for read in a fresh state, and the ratio seen for write or write plus GC is much lower. To summarize, we've described the Radian BTL, our host-resident flash translation layer, and we've discussed how we ported it to SPDK. Because we had designed a host environment abstraction layer, the port to SPDK, which to BTL represents just one more host environment, was straightforward. It was complicated mostly by a few bugs that went unnoticed until the first host environment change, which SPDK represents. We discussed also how performance comparisons that seek to compare different host environments are different from those used to compare different devices. And we've explained why performance ratios observed at the level of the host environment should be greater than the performance ratios observed when a constant amount of additional CPU-consuming storage stack functionality is added. BTL is an example of such additional CPU-consuming functionality, so the performance ratio we observed for BTL plus SPDK versus BTL plus kernel is somewhat less than the performance ratio of SPDK versus kernel without BTL, as expected. In terms of future work, we'd like to look at using the Zone BDEV library as another kind of target that BTL can handle. There are also performance differences we've noticed of certain user space versus kernel space implementations of various host environment primitives, possibly related to context switching and memory performance differences that we'd like to explore further. And we look forward to trying out IOU-ring as a possible basis for yet another BTL host environment when it includes support for all the operations we need, such as reset. This might further reduce the performance gap to be expected between the kernel and SPDK. Thank you.